All right, welcome to lecture 4.6. This is on the graphs of the other trigonometric functions. 4.5 covered sine and cosine, and you have to carry some of that knowledge over that you picked up from 4.5 to be able to wrap your brain around 4.6 here, especially when we run into secant and cosecant, because those graphs are based off of the sine or the cosine function. So we'll go ahead and move forward here. I think we're going to move forward. There we go. Okay, so the objectives for this particular section, we're going to look at the graph of the tangent function and variations on that graph. We'll also look at cotangent, and then we'll round this out with cosecant and secant. Okay, so the first thing that we encounter here in 4.6 is the graph of the tangent function. And on your notes, you'll see I included the unit circle a couple times in this, just like I did in 4.5, because it's just so helpful to have this in front of you so that you don't feel like you're having to reach for a calculator every time you're asked the value of a trig function. And I see that Roy is typing something that helped out a lot. Roy's piece of advice is by all means have your unit circle on your midterm sheet because it does help out a lot. It gives you all of the information, really, well, not all of it, but a good bit of it that you have to know for the chapter 4 material you can pull off of the unit circle here. So I'm glad that you found it helpful to have with you, Roy. Okay, we'll go ahead and look at tangent, the tangent function here. So the first thing, well, let me go ahead and write this on here. I included it on your note sheets, but I'll write it on here that the tangent of theta is given by y over x. And I gave you the whole little chart for all of the trig functions in your notes there, so hopefully that was helpful for you when you were looking through them. But here we go. So we're just going to choose some x values, and the x values that I chose, I took negative pi over 2, negative pi over 4, 0, pi over 6, pi over 4. I should have made that chart a little bit bigger. Sorry, it looks all scrunched up there. Pi over 3. And then I chose a few more values before we get to pi. And I chose 5 pi over 12, which is approximately 1.3. So these are values between pi over 3 and really pi over 2, but I also gave a value for pi over 2 as well. So 17 pi over 36. And that's approximately 1.5. And that knowing the decimal equivalent will be helpful when we put this onto the graph. And then I also chose 89 pi over 180. And I have to admit, I didn't just pull those values out of the air. Your book suggested these. And then this is approximately 1.55. And then I did one more value. I went ahead and did pi over 2, and that's approximately 1.57. Not that you need that, but just showing you how those values live between pi over 3 and pi over 2, numerically speaking there. Okay, so I used the unit circle to get some of these values, and I used my calculator to get others, especially some of the weird ones that we have on the graph here. But remember, the tangent of theta is y over x. So just showing you how I got some of these values from the unit circle. If I look at negative pi over 2, let me get a different color here. If I look at negative pi over 2, I'm talking about 3 pi over 2 if I went in a positive direction around the unit circle, but here I went negative pi over 2 and landed at the point 0, negative 1. Well, tangent is y, which is negative 1 over 0, and this is undefined. So negative pi over 2 is undefined. And so this is how I got these values, or I used my calculator. So I'm just going to go ahead and fill in the rest of this chart. This ends up being negative 1, and then I have 0.6 approximately with square root 3 over 3, and that's approximately 0.6, and then 1, approximately 1.7, approximately 3.7, 11.4, 57.3, and then finally I get back to pi over 2, which is undefined. So notice pi over 2, I would still have, I'd have positive 1 being divided by 0, but it's undefined either way. So what I know about this graph is that I have asymptotes because it's undefined at negative pi over 2 and pi over 2. That means I don't have function that exists there. And we find that we actually have asymptotes that show up there. So just as a reminder, these are lines that the graph will approach but will never actually cross or intersect with. Okay, so I'm just going to put these points on the graph. Let me get a different color. We'll do a green so that it'll stand out against the black here. Okay, so I didn't put all of these points on the graph because I know the general shape, so I just did a few of them to get us going. We have negative, I actually found negative pi over 3. I didn't write it on there, but negative pi over 3 is roughly negative 1.7. So about right here. That looks more like 2, but it's negative 1.7. Now I do know negative pi over 4. Negative pi over 4 is negative 1. So negative pi over 4 is halfway between negative pi over 2 and 0. So I have to point negative pi over 4, negative 1, 0, 0. Here's pi over 4, halfway between 0 and pi over 2. And for positive pi over 4, I get positive 1. And then pi over 3 is 1.7, so about right here. And I could continue drawing these points in, but what you see happening is you get this S-curve. Kind of reminiscent of the cubic function, except the cubic function is not bound by asymptotes. And so there's a picture of one period of the tangent function. So let's talk about the characteristics real quick. So the period, we see this particular period goes from negative pi over 2 to pi over 2, so the full period is pi. We can look at the fact that this thing has origin symmetry happening, but we learned back in the last unit worth of material as well that the tangent function is an odd function. So we get that the tangent of negative x is equal to the negative tangent of x. We are undefined, which also means we have asymptotes at odd multiples of pi over 2. And let's see what else. We have domain. The domain, because we have asymptotes happening through our x values there, we have that your domain can be all real numbers except x cannot be odd multiples of pi over 2, which is where your asymptotes live. So as long as you're not on an odd multiple of pi over 2, you're okay to plug into that function there. And then our range is just negative infinity to positive infinity because we go in both directions vertically unbounded. And the x-intercepts of this function are going to happen midway between the asymptotes. So wherever those, once you start translating in the plane here, those asymptotes are going to shift, but you're always going to cross the x-axis at the dead center between those asymptotes in the horizontal direction, of course. You ready to move forward, Roy? Very good. Okay, so just these next two slides are just background information on how to graph, they say variation, so something that's been transformed or translated, the graph of the tangent function. And we find that our asymptotes live at this expression here. So we have a full period of pi, and your endpoints are going to be determined by setting this expression here greater than your lesser asymptote and less than your greater asymptote. So you find when you can either solve this equation or, inequality as is, just doing whatever you do to the center to both other sides of the equation, or you can split it up and solve it as two separate equations to find those asymptotes. The second thing you're going to do is identify that x-intercept that lives midway between those asymptotes. And then you're going to find points on the graph. Okay, so let me just draw some general asymptotes here. So I have these asymptotes. Let me get another color. And I know exactly halfway between those is going to be my x-intercept. And so this next part says, okay, so find a couple of other points. You want to choose one that's a quarter of the way through and 3/4 of the way between the consecutive asymptotes. In other words, let's say I drew a barrier through my x-intercept here. You're going to half that again to find a point lying on that line and that line. So you're basically halving the halves there. That's why they say 1/4 of the way through and then 1/3 of the way through, because you know the general shape of this thing is to move like that. And so you just need these 2 points to help you find the S part of the curve there. Is that clear for you, Roy, or is that a little confusing the way I put that? Okay, great. And you'll find that the points have y coordinates, and this is important when we calculate this at -a and a. And you know, hopefully this will be clear as mud once we actually walk through a problem like this. And then you're going to use, you know, all the information that you've gathered up here to put it onto a graph. And then if they ask for a larger domain, you'd add any additional cycles to either side of it that is asked by the question. Okay, so this next slide is just a picture of everything we talked about. I didn't have room to put them side by side like I did on your note sheets, but so this is just a visual representation of all that information that we just went through. So let's go ahead and move to the actually working a problem. Okay, so we are asked to graph 3 times the tangent of 2x for a domain of -π/4 to 3π/4. And the first step is to find your 2 consecutive asymptotes. So we want to give our barriers before the function is translated, which is -π/2 and π/2. And we learned on that last page that we can set up bx minus c. And when we solve this, we end up with where our asymptotes for one of our periods lies. So let me just point out what B and C are. In this case, we have an A of 3 right here. We have a B of 2. And because I'm not adding or subtracting anything on the inside of the function, my C is equal to 0 here. Oh, I didn't even see that that was sitting right there. Huh? All right, so let's go ahead and plug in B and C and solve this thing. We have -π/2 less than 2x minus 0 less than π/2. So, of course, that's just -π/2 less than 2x less than π/2. Now, I'm going to divide each term in all 3 areas by 2. However, division by 2 is the same thing as multiplication by 1/2. And since those are in fraction form there, I'm going to multiply by 1/2 instead of dividing by 2. But it's the same exact calculation there. So we end up with -π/4 less than x less than π/4. And you're always going to have matching, well, I don't want to say that. Let's see, would that be correct? -3π/4. Yeah, they're not always going to match. Okay, so from that, we move on to identifying our x-intercept. So I'm going to go ahead and move to the next slide. Okay, so the x-intercepts we had, let me just remind you, we had asymptotes at negative pi over 4 and pi over 4. So on the number line, I have 0, here's pi over 4, and here's negative pi over 4. So sitting halfway between pi over 4 and negative pi over 4 is 0. And remember, we were told that they're the midway between the consecutive asymptotes. So I get that I have an x-intercept at x equals 0. And because we wanted to add another period onto our domain here, let me continue this out a little bit here. We wanted to go all the way up to 3 pi over 4. So just to be clear, I have 0, this is pi over 2. That would make this 3 pi over 4. And if I have asymptotes here and here, then that means I have one here too, because they're spaced pi over 2 apart. Yes. So I have an x-intercept also living right here. Okay, so we have our asymptotes for the domain that we've been asked to work with. We have our x-intercepts with the domain. Now we want to find those midway points, the ones that are 1/4 of the way through and 3/4 of the way through the period. Okay, so this is where it gets a little bit trickier to see what's going on here. What we're told in the information above before we started working on this problem is that the points that are 1/4 and 3/4 of the way through are going to have y coordinates of negative a and a. And in this case, a is equal to 3. So since I have y coordinates here, if I can solve the equation 3 times tangent of 2x, when it's equal to 3 and negative 3, then I will be able to find those x values where the graph lives in its y values at 3 and negative 3. So I'll find those 1/4 and 3/4 points I'm looking for. So we have negative 3 equals 3 times the tangent of 2x. And so what we're trying to do here is figure out what value of x gives us a y value of negative 3. So the first thing I do, of course, is divide off that value, that factor of 3, divides out there. And so now I have negative 1 is equal to the tangent of 2x. Well, if I go over to my unit circle and figure out the tangent of what angle theta is equal to negative 1, because if I can figure this out, I can replace negative 1 there. And I figure out that theta has to be equal to negative pi over 4 for the tangent to be equal to negative 1. So since it's equal to negative pi over 4, I can say that if I replaced if I replaced this 2x here with pi over 4, I'd get -1. That means that 2x has to be equal to -pi over 4, because that's what would give me a -1 tangent value. Have I lost you, or are you good, Roy? Okay, great. All right, so now I'm just solving for x here. I'm going to divide by 2 on both sides, but since I have a fraction on the right-hand side there, I'm actually going to multiply by 1/2. So that takes care of that 2 there, and I end up with x is equal to -pi over 8. So that means I have the point -pi over 8, -3, because that was the y value that I was solving that for. So we do the same type of calculation for 3, a positive a value. 3 tangent of 2x, divide by 3, and I get 1 equals the tangent of 2x. And I find that the tangent of theta is equal to 1 when theta is pi over 4, so positive pi over 4. So pi over 4 equaling 2x, multiply by 1/2 on both sides, and I get pi over 8 is x. So that's the point, pi over 8, +3. So now we have our asymptotes, we have our x-intercepts, and we have a couple of points, one 1/4 of the way through and then the other 3/4 of the way through that can help us get the shape of that curve. So we're ready to put this onto the graph. Okay, so I have asymptotes. I'll do those in green. I have them at -pi over 4. I have them at pi over 4. Use your imagination on the linear aspect of that asymptote there. And then I also have them at 3 pi over 4. Because that's pi over 2 further down the line. And I could continue doing this in both directions if I wanted to, but we'll just show the 2 periods that they've asked for here, the 2 cycles. All right, so I know I have x-intercepts at 0 and at pi over 2. And then I found, remember I had the 2 points, -pi over 8, -3, and pi over 8, 3. Okay, so -pi over 8 is halfway between 0 and -pi over 4. So -pi over 8, -3 lives about right here. And then I have positive pi over 8, +3 living about right here. This is a really skinny and tall curve that comes through here. Whoa, sorry. That's really, really bad looking. Once again, use your imagination on that, Roy. All right, and then I'm going to have the same phenomenon happening because these are identical. So halfway between my middle asymptote and my second x-intercept, I'm going to have a -3 value, and then I'm going to have a +3 value up here, and I can sketch that in. All right, Roy, that is the translated tangent function. How was that for you? Great. Okay, so now we're looking at the cotangent curve. And I chose the values. Let me get my black pen back. Negative pi, negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 3 pi over 4, and 5. And I actually have enough slots in my XY table for everything. Okay, I'm going to go through and point out the undefined. Let me give you this, that the cotangent of theta is equal to x over y. So anytime my y value is 0, that's going to create an undefined situation. So I am undefined at pi, I'm undefined at 0, and I'm undefined at negative pi. So negative pi is going to land you at pi as well. So I'm undefined here, here, and here. And then at negative 3 pi over 4, that puts me right here. When I divide those by each other, I come out with, when I divide the x by the x by the y, I end up with positive 1. Negative pi over 2, I do the division and I end up with 0. Negative pi over 4, I do the division and I get negative 1. Pi over 4 is 1. Pi over 2 is 0. 3 pi over 4 is negative 1. So when we get into this, we figure out that we've got asymptotes, and you can see where our asymptotes live. I have one at negative pi. Negative pi. I have one at 0. And then I have one at pi for the domain that we've moved through. So you can see that we have a period of 1 full pi. All right, I have the points. Get my green back here. I have x-intercepts at negative pi over 2 and pi over 2. My y values were 0 there. Negative 3 pi over 4, 1. Negative pi over 4, negative 1. So this comes in like this. And then you go here. It makes that sound too when you do it here. Okay, same thing here. I have positive pi over 4 and positive 3 pi over 4. So we come down like this, pass through, and then approach that asymptote. Okay, so that is the general cotangent curve. We have a period of pi. We have that this particular function is an odd function, so it has origin symmetry. You can see that. The cotangent of negative x is equal to the negative cotangent of x. So that tells us it's odd. It's undefined at integral multiples of pi, which are also where your asymptotes are. So it's undefined. In other words, it has asymptotes at integral multiples of pi. So the reason they say integral is because if you shifted left or right, you may not be exactly on pi. So they're just the asymptotes land pi distance apart. And x-intercepts, we have x-intercepts halfway between the asymptotes. And then finally our domain is all real numbers except x cannot be those integral multiples of pi. So I'm just going to put im pi for integral multiples of pi. And then our range, you can see, is negative infinity to positive infinity. Whoa. All right. Okay, so same thing that we had last time here. We have that we're going to have asymptotes at the expression bx minus c when that lives greater than 0 but less than pi. And you can either solve that simultaneously as the inequality or set it up in its separate pieces as an equation. To identify x-intercepts, those are going to be midway between your asymptotes. You're going to find that quarter and that 3/4 of the way through points as well, using the function equaling to a and negative a, just like we did in the last one, and then you'll graph. And here's a picture of all of that information there for you. Okay, so the first thing we want to do is find our two consecutive asymptotes. So we have 0 is less than, here's the expression here that I'm following. In this case, our b is pi over 2. X minus 0 for our c, and that is less than pi. So that's 0 less than pi over 2x less than pi. And now to get that pi over 2 off of my variable on the inside, I need to multiply by 2 over pi. So everything gets multiplied by 2 over pi. And we end up with 0 less than x less than 2, because those pi's divide out right there. So we have asymptotes at 0 and 2 for this particular graph here. And then we find that our x-intercept lives halfway between 0 and 2. Which puts us at an x-intercept of 1 there. Okay, now we're ready to find our quarter of the way through and 3/4 of the way through points. Let me just point out that A is equal to 1/2 here. So we want to set up the two equations. Negative 1/2 is equal to 1/2 the cotangent of pi over 2x, and 1/2 equals 1/2 the cotangent of pi over 2x. Okay, so we're just going to solve these two real quick. Dividing by 1/2 on both sides is the same thing as multiplying by 2 on both sides. So I have -1 equal to cotangent of pi over 2x. And we find that the cotangent of, when the cotangent equals -1, so the cotangent of theta equaling -1, that means theta had to be equal to 3 pi over 4. So I can set 3 pi over 4 equal to pi over 2x, multiply both sides by, let me get my pen, 2 over pi, squeezed it in there, 2 over pi, to get rid of those. And when I finish this off, I get 6 pi over, no more pi's. Sorry, my pi's divide out there. 6 over 4, which is equivalent, this is 6 over 4, which is equivalent to 3/2. So that calculation right there gives us the point 3/2, -1/2. And then do this other equation here, solve this other equation for 1/2. And I divide 1/2 on both sides, and I get 1 equals the cotangent of pi over 2x. I find that the cotangent of theta is equal to +1 when theta is equal to pi over 4. So I can set pi over 4 equal to pi over 2x, multiply by pi over 2x on both sides. No, not pi over 2x, 2 over pi. Those divide out, and I have that. My pi's divide out as well. 2 over 4 equals x, that's 1/2. So here I have the point 1/2 and 1/2. Okay, so I've got my 2 points that are on either side of my x-intercept. I'm ready to put this onto a graph. Let me get a thicker pen here. First thing I'm going to do is mark my asymptotes, and I had an asymptote at 0. That's why I grabbed a thicker pen since it's right on the y-axis there. And 2. So 2 is roughly about right here, because I know pi is 3.14. Pi over 2 is like 1.57. So maybe about right there. And you can use your imagination as usual. Let me mark 1 on my x-axis. My 1 is about right here, and this is 2. Okay. So the reason I marked 1 is because that's where my x-intercept is, which is the next thing that I have to graph. Remember, that always falls halfway between those two asymptotes. And then I also have the point 1/2, 1/2, and 3/2, -1/2. So I follow that asymptote without crossing it, and then swoop over, and then approach that other asymptote. All right, so there's one period of the translated cotangent function there. You good, Roy? Excelente. Excuse me. All right, so these are actually blanks on your note sheets here. If you want to fill those in if you're following along. We obtain the graphs of cosecant and secant curves by using the reciprocal identities. We learned a few sections ago that the cosecant of x is equal to 1 over the sine of x, and the secant of x is equal to 1 over the cosine of x. So what we actually do is for cosecant, we end up graphing the sine of x, and then we use that graph to sketch the cosecant, and just the opposite with secant. So you have this sine or this cosine curve coming through here, and what ends up happening when we look at it, we see that the inverse of these make these U shapes at the maximum and minimums of either the sine or the cosine. So you're going to be making the same type of picture with cosecant and secant. It's just going to be shifted because we know that sine and cosine look exactly the same, except that they just start at different places. And when I say start, I guess I mean like starting their period either one above the x-axis or on the x-axis. Okay, so this is a picture of the cosecant curve. So what I'll point out here is that this is the sine curve weaving through here. And you can see what I was talking about. The cosecant makes this U shape approaching these asymptotes, but it shares either a maximum or a minimum with the sine function the whole way through. So we get that the period, just like the period for sine is 2 pi, we get the period for cosecant is 2 pi. The domain is all real numbers except for those integral multiples of pi, because we can see that we have asymptotes sitting at those integral multiples of pi. Your range, all real numbers, such that y is less than or equal to -1, greater than x. So this is a much more concise way of saying this by just using your interval notation there. So we have a range from -infinity to -1 and 1 to positive infinity. And I have on your sheet x-intercepts, that's not applicable there, and it's undefined and has vertical asymptotes, it does integral multiples of pi. Okay, so now, instead of having the sine function weave through, we have the cosine function, but you can see this picture looks almost the same as the last. So there's not much different to talk about here. We have a period of 2 pi. We have a domain of all real numbers except for odd multiples of pi over 2. So our domain is all real numbers. X cannot be, though, odd multiples of pi over 2. This is an odd function here. We have origin symmetry happening. Our range Well, you can see if I draw these barriers here, we're never going to go between +1 and -1 in the y direction. So our range is -infinity to -1 inclusive, or 1 to +infinity. And no x-intercepts to worry about. We are undefined, or we have vertical asymptotes that odd multiples of pi/2. Oh, I'm sorry. That was the cosecant I was still talking about. So that was still sine. This is secant, but you can see why I got confused. I wasn't paying close enough attention because it's the same dang thing, except just shifted over. So I'm not going to go through all this because I just gave you all the information for cosecant, but here's the picture of it. And same there. So now we're ready to sketch. So notice the word sketch. What you're actually graphing when you graph cosecant or secant is the sine or the cosine curve, because that gives you your starting point to then go back and sketch in those U-shapes at the maximums and minimums. So this is a blank on your sheet here. The x-intercepts of the sine graph correspond to the vertical asymptotes of the cosecant graph. So the x-intercepts of the sine graph, I'll point those out, correspond to the vertical asymptotes for the cosecant. Okay, so I'm asked to sketch the graph of cosecant, and I use the graph of x, sine of x plus pi/4. Now, with this particular problem, they went ahead and gave you the graph of sine of x plus 4, but on the next one we do, we'll actually find the graph of the cosine, and then we'll sketch the secant. But this one, we're just practicing the sketching part. So what I need to focus on are the maxes and mins I have here of the sine function. So for what we're looking at here on this graph, I'm going to have a U following that asymptote, touching that maximum, and then following that opposite asymptote all the way up. And then I have this upside down U doing the same type of thing except with the minimum. And my graph ends there. So that's sketching the graph of the cosecant curve there. Are you good with that, Roy? Okay, great. And like I said, the next one that we do will actually not start with anything on our graph and go from there. Okay, so we are asked to graph, in this case, 2 times the secant of 2x. But what I really have to do, I mean, this is the sketching part. What the real work is in getting 2 times the cosine of 2x. on the graph so that I can use that curve to get my key points to help me put the secant function on the graph. So I'm going to actually follow the steps to graphing the cosine that we learned back in 4.5. And the first thing we have to find is the amplitude. And we find that the amplitude is the absolute value of A. In this case, A is 2 and B is 2. C is 0 there. So I have the absolute value of 2, which is 2. And I also am given back in 2.5 that the period of the cosine function is given by 2 pi over B. So that's 2 pi over 2 in this case, which is just pi. So I have a period of pi happening here. And then we're going to use quarter periods because we know the quarters are those key points. Halfway between is where our cosecant, where our secant curve touches that maximum or minimum. But on our cosine function, it will actually give the maximum or the minimum halfway between those periods. And then we'll do the quarter and the 3/4 as well. Okay, so we'll start at 0 and go all the way up to pi. And so that'll put us figuring pi, oops, my keypad's in the way, pi over 4, pi over 2, and 3 pi over 4. And just a reminder, this is a chart for the cosine, not the secant. Remember, we just sketched the secant. This is the actual graphing part that we're doing. So we have y equals 2 times the cosine of 2 times 0, because it's 2 times x, and I'm plugging in 0 for x into this one. So that's 2 times the cosine of 0. The cosine of 0 from our unit circle is 1. So this gives us the point 0, 2. All right, y equals 2 times the cosine of 2 times pi over 4, which is 2 times the cosine of pi over 2. The cosine of pi over 2 is 0, so we have the point pi over 4, 0. Y equals 2 times the cosine of 2 times pi over 2, which is just 2 times the cosine of pi. The cosine of pi is -1. So we have pi over 2, -2. Remember, we had an amplitude of 2, so you can see that we've had the 2 and the -2 show up there. Y equals 2 times the cosine of 2 times 3 pi over 4, which is 2 times the cosine of, let's see, that's 6 pi over 4, which is 3 pi over 2. And the cosine of 3 pi over 2 is 0. So we have the point 3 pi over 4, 0. And then finally, we have y equals 2 times the cosine of 2 times pi, which is just 2 times the cosine of 2 pi. The cosine of 2 pi is 1. So we have the point pi 2. We're ready to put our cosine curve on the graph and then sketch our secant. Okay, so the first thing I'm going to do is put my, I'm gonna mark my asymptotes for the secant function. And I find that I have asymptotes at pi over 4. Actually, no, I don't put my asymptotes on first. Let me go ahead and just graph my cosecant function here. I have the points. Let's see, 0, 2, pi over 4, 0, right here, pi over 2, negative 2, 3 pi over 4, 0, and pi 2. So we have this happening, and this is our cosecant. This is not, I'm sorry, this is our cosine, not our secant function here. And we find that, and this is, I forgot to put this on the PowerPoint here. I have some blanks up at the top of the page, and it says, note the x-intercepts of the sine. Oh, I'm sorry, that was the last page. My eyes are going crazy. I don't have anything else at the top of this page. Okay, so we do have vertical asymptotes that live at the x-intercepts of the cosine function. So I have a vertical asymptote here going through that x-intercept of the cosine function, and an x-intercept here. I had to run to the side there to meet that x-intercept. So I could keep doing this and do more periods if I wanted to. Like there'd be an asymptote, and I'd have another asymptote here. So the problem asks us to graph this for negative 3 pi over 4 up to 3 pi over 4. So let me just point out that this right here is 3 pi over 4. No, it's not. That's too far. Because that's not even pi, and I'm past pi on my graph. 3 pi over 4 is here. And negative 3 pi over 4 is here. So I will put another asymptote, because if I continued my sine curve, I'll go ahead and do that. If I continue my sine curve, I'm going to pass through here. I'm going to go down and touch 2, and then come back up through there. So I have another asymptote there at negative 3 pi over 4. Okay, so I'm going to erase this because I don't need to go that far. All right, so I have my cosine on my graph. Now I'm ready to go and sketch my secant. And all I need to sketch my secant are my maxes and mins contained on the graph, because I know it's just a U shape that touches either the maximum or the minimum and then follows the asymptotes. This is a really bad graph. That's what I get for trying to freehand stuff there. All right, so the blue part is the sketch of that particular secant function. Do you have any questions about that, Roy? Okay, Roy's ready to move on. Okay, so there's nothing left to do per se in this lesson, but I did want to include just sketches of the 6 curves of trigonometry just for reference sake. So here you're looking at the sine function. Remember, you can remember the difference between sine and cosine because cosine starts at starts at +1 and then coasts down. So you can know that you're looking at the sine function here because it starts at the origin or goes through the origin. So there is the sine function. There's the cosine function coasting down. You have your information on domain, range, and the period. Then we have our new ones. We have our tangent function. Cotangent function. Sorry this is taking so long, Roy. It takes forever for these slides to move forward. Here is the cosecant function, and I'll point out one thing here. This is the one that goes with the sine curve. So my sine curve comes through like this. And here, and so on. And lastly, I have my secant, which is the inverse of cosine, which comes through like this. And that's all I have for you today, Roy. If you don't have any questions, I'll just tell you to have a good weekend. And next lecture will be next Wednesday over 4.7. You do the same. Thank you, Roy. Have a great weekend.